Welcome to More Learn, More Teach, where I attempt to simplify the complex. We're going to continue on with our concentration series with a problem here. We have a tank A, which has a volume of A concentration of A of some solute solvent mix. We have another tank, which is B, with its set of parameters. Has some valves that are open. There's some volume, some volumetric flow rate that is flowing into another tank. This tank will have a volume and a concentration. It's also leaking, so I have some volume of liquid leaving this tank. So we're going to attempt to solve what the concentration is of this liquid at equilibrium. Equations we're going to use to solve this problem. Concentration is equal to mass of the solute divided by the volume of the solution. Therefore, if I rearrange it, the concentration multiplied by the volume is going to give you the mass of the solute. This is going to be important because we're going to be doing mass balances on the solute. Volumetric flow rate, the V dot, volumetric flow rate, is going to be the volume as a function of time. Volume flow is a function of time. And mass will be conserved. Our assumptions. So these equations are true. These assumptions may or may not be true, but for this problem we are solving, we're going to make these assumptions. If this were a real problem, we would have to test these assumptions and validate these assumptions. But since this is made up, we'll go with it. Uniform mixing. That means that the concentration at the bottom of the tank is the same as the top of the tank. All throughout, we have the same mixing. Concentration is not gradient, it is constant. Uniform mixing. Instantaneous mixing. I'm saying that we are instantly going to equilibrium. No change in density of the solvent. There is no temperature pressure changes between these to compress our solvent. And there's no chemical reactions. All right, so now we have our equations and our assumptions. We can solve for this concentration. We're going to do that with a mass balance. We're going to do the mass balance of the solute. So that is going to be conserved because we have no chemical reaction. If we had a chemical reaction, that would be different. So no chemical reaction means that the mass flowed from A plus the mass flowing from B minus the mass that leaves the tank must be the mass that accumulates in the tank. So conservation of mass. Mass of the solute that flowed from A plus the mass of the solute that flowed from B minus the mass of the solute that left must equal the mass of the solute that remains. The concentration multiplied by the volume, that's going to give me mass. So the amount of solute that flowed from A is the volume that flowed from A multiplied by the concentration of the tank that it flowed from. The mass of the solute from B is equal to the concentration of the tank of B multiplied by the volume that flowed out of B. It's important to note, this is not the volume of the tank itself. This is the amount of volume that flowed from the tank into C. The mass of the solute that left is equal to the concentration, whatever that is, at equilibrium of C, multiplied by the volume that flowed out. This is only true because we assumed instantaneous equilibrium. If it's not instantaneous equilibrium, then this doesn't hold, right? But instantaneous equilibrium allows me to make this approximation. So this equals the accumulation in the tank. What's there? The concentration, the equilibrium concentration, multiplied by the volume that's there. That is the mass of the solute in tank C. So this would be a static equation, right? This would be an accumulation equation. But I want to know as a function of time, right? I want to know dynamically what is happening to the concentration of that tank. So if I divide both sides by time, if I divide this equation and this equation, if I divide this side and this side by time, I have not changed the equation. However, now I have converted us from a static in time event to a dynamic event that changes with time. So dividing both sides by time. If I divide both sides by time and then group the time with the volumes, I can rearrange to the parameters that I had in my starting problem set. So I end up with the concentration in tank A multiplied by the volumetric flow rate from A. By the way, this would be the mass flow rate from A into C. So this plus the concentration of tank B multiplied by the volumetric flow rate out of B minus what's leaving the tank, which was the concentration of C multiplied by the volumetric flow rate or the leak rate out of C. That is going to equal to my concentration multiplied by my volume divided by time. So this will give me a accumulation as a function of time. So now rearranging this equation, I end up with the concentration of C multiplied by the accumulation rate of the tank plus the concentration of C multiplied by the leak rate, the volumetric flow rate out of the tank, is going to equal to the concentration of A multiplied by the volumetric flow rate from A into C plus the concentration of B multiplied by the volumetric flow rate from B into C. Now I can group and I can say that the concentration of C multiplied by the summation of the accumulation rate plus the leak rate must equal to the concentration of A multiplied by the volumetric flow rate of A plus the concentration of B multiplied by the volumetric flow rate of B. Rearranging, my equilibrium concentration is going to equal to the concentration of A multiplied by the volumetric flow rate of A plus concentration of B multiplied by the volumetric flow rate of B, all this divided by the accumulation rate in the tank plus the leak rate of the tank. So now we have a relationship between these variables, so these parameters in our equation. So we have now we've developed a relationship between these parameters and the concentration in this tank that's accumulating. I can now look at how qualitatively how this changes. I could also tie in numbers and make it numeric, but qualitatively we can have an understanding of what things we can change in order to have an effect on this concentration. So let's say that all things being constant, I just changed the volumetric flow rate from tank A into C, how would that affect the concentration of C? So what does that mean? That means that the accumulation rate in the tank is constant. The leak rate is constant. The mass flow rate from B into C is constant. The concentration of A is constant. But we now increase the volumetric flow rate of A. So if we look at this, we have kept the denominator constant, but we have raised the numerator. Okay, because I have a bigger number now added to a constant, that's going to give me a bigger concentration. So that means that if the volumetric flow rate of A goes up, then the concentration in C would go up. Okay? So looking at this, we could see that these are just variables. So A and B in my expression really doesn't matter which one's which. So I would get exactly the same relationship if we kept A constant but increased B, we would get exactly the same relationship. So what this has told us, what this important thing this has told us is that if I raise the volumetric flow rate from either tank A or B, or the combination of both, then I am increasing the concentration of C given an accumulation rate and a leak rate. All right, let's look at another relationship. Let's say that for a given volumetric flow rate of A given volumetric flow rate of B, a given accumulation rate, I now increase the leak rate. What does that do to the concentration in the tank? So what I've described here is no change in the concentration of A, no change in the volumetric flow rate of A, no change in the concentration of B, no change in the volumetric flow rate of B, no change in the accumulation rate in the tank, but I have increased the volumetric flow rate out of the tank, or the leak rate. What does it do to the concentration? So we can see that the numerator remained constant, but the denominator is getting bigger. So if the denominator gets bigger, but the numerator remains constant, then that must mean that this gets smaller. So we have an inverse relationship because these factors are in the denominator. So anything that happens here will inversely affect this concentration. So increasing the volumetric flow rate will decrease the concentration in the tank. We know that if the leak rate out of the tank goes up, then the concentration in the tank must go down. We can, of course, do this same analysis for many different factors. If I change the concentration of A, what effect would that have? Well, if this goes up, everything else remains constant. It's in the numerator. The numerator gets bigger. For a constant denominator, this will get larger. Same is true for the concentration of B. Now, if I had parameters changed here and here, we would have to look at that individually, and that would be possibly a numerical analysis. It'd be difficult to do that qualitatively. You probably want to do that numerically because the ratios would matter, right? In the bottom, anything that makes the bottom go up but keep the top constant. So if the numerator remains constant, the denominator goes up, then the concentration would go down, which means that if my accumulation rate goes up, so the level of the tank is constantly getting higher, if that gets bigger, if that goes higher, then I'm going to have less concentration. So I have an inverse relationship between the accumulation rate and the concentration. That could be balanced out by the leak rate, right? If I had multiple parameters that changed, let's say that the flow in was constant, so therefore the numerator is constant, then that could mean that to keep a constant concentration for a given accumulation rate, I would need to balance it out with a different flow rate, the opposite flow rate, right? If this goes up, this must go down. Thank you for watching my video. Please like and subscribe. If you have any questions that I can help you out with, I'd be happy to try and answer your questions. Send me an email at morelearnmoreteach@gmail.com.